All right, we are at 95 degrees Celsius. I turned off the stirrer because you can start to see it's boiling in there. It's just a gentle boil. There's not very big bubbles. But as this gets, like I said, as this continues to get higher and higher, it's at 96 right now. The bubbles are going to get bigger and bigger as it gets closer to 100. So here we go. This is a physical change. The water is not changing at all in this particular demo. All right, all you're doing is you're heating it. You're changing it from a liquid into a gas. If you were capturing the steam coming out the top, you could cool that steam down and it would condense and turn back into a liquid. So by adding temperature, you change it in from a solid to a liquid to a gas. By removing thermal energy or cooling it down, you change it from a gas back to a liquid, back to a solid. So right now it's at 98 degrees. Pretty soon it's going to stop increasing in temperature and it's just going to boil. $99 degrees. We're getting a rapid boil now. You can see it in there. And you can see the steam coming off the top. All right, depending upon the thermometer, that may or may not be the peak, the top. Sometimes the thermometer isn't calibrated right. The water is boiling, which means it is at 100 degrees Celsius. The thermometer is reading about 99.5. So like I said, it might be a calibration issue. So even though the temperature on this is 450, that hot plate is 450, the water will not go above 100. So this device is an example of a chemical change. This is an electrolysis machine. Now this one I made. It's a Ziploc bowl that I had poked 2 holes through and shoved pencils through, and then I used hot glue to seal it up. And I sharpened both ends of the pencils because when you plug electricity in, the graphite in the middle of the pencil conducts electricity. So the electricity from this 9-volt battery is running through the wires and into the left and the right side and is splitting this saltwater solution into 2 gases, oxygen and hydrogen. And the reason that I know that is because on the left, oxygen, there is about half as much as the one on the right, hydrogen, and that's because in a molecule of water, there are 2 hydrogen atoms for every 1 oxygen atom. So when you electrolyze water like this, you get twice as much hydrogen as you do oxygen. So this is H2O. In this container, this is pure oxygen right now, and this is pure hydrogen. And if you look, you can see right there, bubbles going up the top. That's bubbles of hydrogen. And there's bubbles on this side too, bubbles of oxygen being made as the salt water is electrified, and on the tips of each pencil, it is making gases. All right, this is a chemical change. I could get the water back. If I combine the oxygen and the hydrogen and I added a spark, it would cause an explosion and make a very small amount of water vapor. But because I am changing the water into its component chemicals, into its component elements, this is an example of a chemical change. This has been running for 23 minutes now. There's a heating pad on this side that's been warming up the bottom right-hand side of the camera. the bottom right-hand side of the fish tank, and there's a container of ice that's been cooling down the top left of the fish tank. So I'm going to inject red food coloring into this side, and I'm going to inject blue food coloring into the other side. And hopefully, if this works right, we should see currents flowing through.
Which is a current.
If this works, then the red food coloring should rise and move from the right to the left. So we should see it rise up and start to flow that way. And as it gets to the ice, it's going to cool down and drop. The blue should flow across the bottom of the fish tank, but once it gets to the red, to the heating pad, it should rise up. So we should start to see a vortex. So the blue sank straight to the bottom and is moving from left to right. You can see.
Why just 24 minutes?
Because I started it 24 minutes ago without the food coloring because I wanted the water to start mixing. And then the red, you can see it starting to move from right to left, sort of in the middle. For some reason, every time I do this, I don't get complete mixture, but I'm getting a current, a convection current of warm water rising and cold water sinking. The warm water is going to go above the blue, so you're going to see the red go on top of the blue, and then it's going to start in a circular mixture. For some reason, the blue is flowing and pushing the red out of the way. I don't know if the red food coloring is a different density than blue food coloring.
Yes, it is possible because we made from different.
But it's moving faster over here now. Like this part up here is rising faster and moving over faster. So you can see the red swirls.
Yes, I
Once
see.
it gets over there, it starts moving slower. And it's been running for 34 minutes.
Particles of warm water move faster. Particles.
Well, they spread apart and they get less dense, so they rise. When they cool off, they slow down and they get closer together, so they become more dense and sink. So this is low density and that's high density, and that's why this is moving the way it is.
But you see, when you put here blue, there is anything here, but here there is red.
Yeah. Because the blue is pretty much sticking down at the bottom, except for the little bit that's mixed in and is flowing with the current. I'm going to stop it. It's been 35 minutes and it seems to be nicely mixed.
What time is it? Oh, 55.
This has been running for 12 minutes. All right, so for station 1, I've got a tank filled with water. And on the bottom of the tank and also along the side of the tank, I've got graph paper so that you can see lines. And the reason that we're going to do that is I'm going to be shining a laser inside the graph paper or inside the fish tank. And I want you to be able to see that the laser is traveling along a straight line. So for the first one, I've got the laser over here. And what's going to happen is it's going to follow this line right here, right? So as it goes along, you'll see that it's following that line. And as it goes into the tank, you see, it doesn't follow that line anymore. It refracts because the laser goes from one material, one media, in other words, the air, into plastic and water, and they have a different refraction. So you're getting a bent angle. Let me see if I can get this down. See, unfortunately you can't see. All right, and you also see some of the laser light is being reflected off of the angle, and some of it's being refracted inside the tank. All right, one really cool thing that we discovered is if I shine this in here and I angle it there, do you see how it's internally reflecting? So you're getting a little bit of internal reflection off of the left panel and a little bit off the right panel. There it is too. So it's bouncing off of the panel closest to me, and the angle of incidence, the angle of the beam coming in, is equal to the angle of reflection. So you're getting equal and opposite bounce. You can even see that on the graph paper. There's equal area under each of the curves, as your math teacher would say. Looking at it from this angle, if I shine it in, watch what happens when I go to the surface. See, it's reflecting off of the surface. And I've even been able to get it to where it reflects off the surface. There. So it's reflecting off the surface, and then off that wall, and then off that wall, and then going into the back. So I'm getting 4 points of reflection. And if you look over here, you'll see that. It's going up, bouncing off the surface, coming down, hitting the wall right there where it's bright, going back over there, hitting that wall, and then in the back going against there. So 1, 2, 3, 4, 5 points of refraction. All right, of internal reflection. Sorry, internal reflection. That's what that phenomenon is. That's the surface of the water right there. See, there's the edge of the water right there. So that's the surface of the water, and if you angle the laser just right, it is reflecting off the inside. So don't forget, as the light passes from one media, in this case air, into another media, in this case water, it looks like it's bending. And in fact, it is bending. It is refracting. All right, so here it is coming in straight, hitting that, angling maybe 20 or 30 degrees, and then going up. So if you look, see, it's going in right on that line, and it's coming out right on that line, but then it angles up, and it goes up. Let's see, rise over run in this case is, it goes up 2 blocks, and it's over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 blocks. So rise over run. It runs 12 blocks and it rises 2 blocks. So those of you that are in algebra and geometry, you can use rise over run to figure out the slope of that line. It should be a straight line, but because of refraction, it is not. Refraction is different than reflection. Reflection is bouncing off of a surface. Refraction is bending as a result of moving from one media, in this case air, into another media, water. So then for the last one, I've got a white light here, and this is a diffracting gradient. Whoops, it's upside down. This is a diffraction gradient, and what this does is it takes that white light and it splits it into the colors of a rainbow. So for the question number, I believe it's 3 on your paper, it says to draw the colors in as they appear through the diffracting gradient. You're going to draw in all the colors that are not there except for when you look through the grading. So make sure you color those in and draw those in. All right, now they appear to be big rectangles because the source of light is a big rectangle. So you can just do bands. You could do red, orange, yellow, green, blue, and then purple or violet or indigo or whatever you want to call it. All right?